Welcome back to the channel. Over the past three videos, we've looked at the mass spec data for E. coli, so a single bacterium on a single spectrum, and we've done a lot of data processing. We've done peak picking, we've done baseline correction, and we've done signal filtering. And so in this video, I want to show you how we can convert what we applied to a single mass spectrum to all of the mass spec data by converting our methods into our own customized functions that we could then use to loop through the entire data frame. So in the original video, we imported from pkutils this baseline function or this baseline method to compute the baseline of the mass spec data. That's what we are doing here, and we're computing it for a 6th-degree polynomial. In this line here, we take that baseline variable, we subtract it from the original mass spec data, and thus we can correct the baseline by subtracting the baseline from the signal and getting a flatter mass spectrum. Now, the way we implemented this will only work for a single variable, a single column of data, but in this single data frame, there's actually more mass spec data. We have replicate injections of E. coli and several other bacteria that we want to then apply the same treatment to. On the right side of the screen now, I've developed this module called Bacteria Processing Methods, and it has all of the methods that we've used over the past three videos: our signal filtering, our peak picking, and our baseline correction, but written in a way that allows us to apply it to the entire data frame. And so here is the example for the baseline correction. We have a function called baseline correct. It takes in a data frame. I have some documentation. I'll actually include the link to the GitHub so you can read this in more detail. But what we do is we take our data frame, we create a new data frame called new df, and we're going to use that index value so we can make sure whatever we do the transform on, we can match the index value to. And the secret to this is really this df.items. The df.items method allows us to iterate through each of the columns in this data frame. And in our case, each column will be a different mass spectrum for one of our samples. From that, we output two variables, one I being the index and the second being the values in that column. We'll then run this very familiar line here, which we compute our baseline using a 3rd-degree polynomial. We'll subtract that from the values, our mass spec data, and then we'll append our new variable to the column called new df. And once we've iterated through all the columns, we'll output our variable called new df. So in this module, we have several methods. We have one for peak picking called getPeaks. We have another called getLabels that'll just clean up the labels on this data, since we're going to be appending these tags called filtered or baseline correct. We have some of the other functions here for smoothing the data. You can see each time we do that, we add some new tags, so we have a sense of what we've done. And so in this video, we're really going to focus on how we can build out our own data processing pipeline for this entire data array. Let me show you. So here is the primary notebook for the video, where we are now importing a number of libraries you've seen many times before. And the key library in this video is this bacteria processing methods. That's the one I just showed you that has all of our methods that we've used, written out, and converted to our own functions. I have this gram dictionary that will allow us to look at each bacteria and determine the gram state. Is it gram negative or gram positive? And this is largely for the data viz at the end of the video. So stick around so you can see how we can leverage these data processing pipelines with our PCA, and then showing how these data cluster. Next, we'll find the data on my hard drive, and then we'll do a little bit of cleaning pretty quickly. So this is that full data table that we've been looking at over the past few weeks, where each column is now a different mass spectrum from several bacteria. We have our master charge column. And so the first real step here is to clean that up. That's what we do here. We replace this / with empty space. We get rid of some of these extra spaces and replace them with underscores to get a cleaner data table like this. This is oftentimes one of the first steps, because now it's easier to remember the formatting of our data, and this is far more Pythonic. I want to show you what the first few data points look like. So this is the data before we've done any of our processing. This looks like a typical mass spectrum, fairly low resolution that is. And so this instrument actually is a small shoebox sized mass spectrometer. And so for that reason, the software isn't that well developed. So when I was originally processing this data, I actually couldn't do this. And so it's really cool to go back and look at it. And so what we have here is mass spec data from master charge 400 to 800. Out here in the 650 to 800 region is where most of our lipid signal is found. Maybe it's the smaller fatty acids here, but these are all for this WAFI samples. There are several more. Let's say if we look at maybe the next, another set of 5, we have a lot of the physalis and facium samples. And so you can see here that there's a lot of data in this data table, and thus once we can process this, we can then develop some nice visualizations from this piece here. So I want to show a number of different processing chains. Our data is called X, and this is not the structure of the data if you want to do data modeling. And so our first step will be just to transpose this data, and we'll just store that as X1. So our first sort of minimally processed variable will be X1. The next thing we'll do, let's make X2, which will have a little bit more extensive processing. Let's train our methods. Actually, let me show you this first. Let's take X, and we're going to process it this way by piping our methods together now. So when we run pipe, we can pass our methods. And I should state that when we import using this asterisk, I can just call the methods in this library by their name. Generally, this is not advised, but because I've given them unique names and the scope of this project is somewhat narrow, it's okay, but you wouldn't want to use this import asterisk for pandas or numpy because those are just such large libraries and it's generally ill-advised. And so I'm just doing this here, maybe not the best practice. Let's take one of our methods. Let's start with smooth data. So we can pass in smooth data. When you run pipe, you just pass in the method or the function. You don't need extra parentheses. And in the comma here now is where we would apply any keyword arguments to the smooth data method. And so smooth data needs a window size or window length that equals 7 in this case. And let's set our poly order to 3. And so as you can see, when we run this smooth data, we return a new data frame, and we've added this filtered sort of tag on it, so we know we've now filtered the data. That is what I showed you in our original library. And so this is a step where all we've done so far is just filtered the data. And let's do one more thing. Let's also pipe our transpose method. Let's also pipe our baseline correct method. So let's run baseline correct. And again, these are coming out of that library we built, and we don't need to pass anything. We'll just use the default third degree polynomial. And the last thing we want to do is just transpose so that our data is in the right structure. If you look at that, you see we now have a data structure that's the same as X1, and we'll set this as X2. X3 will be a bit more extensively processed. We'll use more steps, and you'll see why. Let's do the same approach, or we can sort of track this process. And so we're going to have our pipe, and let's just copy this. There's no point really in rewriting everything. But what I want to do before the transpose is to pipe the peak picking feature. So let's call it get peaks, and let's pass in that prominence. In the other video, a prominence of 150 was pretty nice, and a peak width of 5 also was a pretty good point. And so you can see that here now we have data that has been filtered at baseline corrected. There is no there's no underscore for the peak picking. And let's save this as X3 equals that. And so we have a data frame that's been minimally processed as transposed, one that's moderately and one that's maybe more extreme. Let's run this. And I want to show you how we've maybe manipulated the data. And so when we look at display, we can look at x1.shape, x2.shape, and x3.shape. And when we look at this, you see each sample has 54 rows. We don't expect that to change. The first sample has 401 variables that we know came in from our original data set. The second data frame has 401 as well, because all we've done is baseline correct and smooth the data. But the third data frame, X3, has 54 variables. So when we run this get peaks, we're actually now filtering the data. Again, check out the GitHub if you want to see how this is working. But in short, the way this works is that if there is a peak in any of the samples, it'll look for that peak in all the samples. But if there is no peak in any of them, it will actually drop that variable out based on these peak picking conditions. And so here can really affect what your data frame looks like. So let's make a list. Let's call this X list. And we're going to make a list of our X parameters so we can actually loop through and look at what the PCA looks like for each of these. So we're going to loop through here. And I'm going to switch this to side-by-side mode just to give us a different view for what this output's going to look like. And I want to loop through each of these. And so let's say for X in X list, we're going to compute our score values. And so we know how to do this. We can just run get PCADF. And we're going to compute it for X. Again, X is going to be one of these data frames based on this for loop. We also want a column variable. So when we build our scatter plot matrix, we have a way to select which columns we want to plot. And so this will just be scores.columns. Next, let's make a label. And this will allow us to color the points based on the bacteria class, so gram negative or gram positive. And that's how we have our get labels method. So we can remove that tag. So recall each of these has like a baseline correct tag or filter tag, but our dictionary does not have it at. So we need to get each of these column names back to a key in our dictionary. And that's what that get label does. It actually cuts at those underscores and gets us back to that original name. And then let's make our figure. So figure equals px.scatter. Let's run scatter matrix. Score will be our data frame. Dimensions will be the points, will be the variables used in the scatter plot matrix. So color will look a little complicated, but just rewatch this section and it should get more clear. If you want a video specifically on this map, I would be happy to make one. But essentially, we're going to map our dictionary to that labels column so that we can go from the bacteria name to the bacteria gram state, gram positive or gram negative. And then lastly, let's run fig.show. So every time for each data frame, we're going to compute our PCA. We're going to generate these variables that we'll use to color in our scatterplot matrix, and we can then see how each of these clusters and how well those clusters tend to correspond with the state of the gram positive or gram negative nature of the bacteria. So let's look at the first one. So this first one would be the data frame that was least processed. And if we look at the first three principal components plotted, we see it does look okay. If we look at like PC1 versus PC2, it looks decent. We can actually see that, let me get out of side-by-side mode. We can see that we do have some separation based on the gram state, so gram negative versus gram positive, and this is the one that has had no data processing. If we look at the second one where we've done some filtering, we've corrected the baseline, I'd say we have a little bit of better clustering between gram positive and gram negative. And again, this is unsupervised, so we haven't told it how to separate. This is just separating based on patterns within the data that appear to correspond with gram positive and gram negative. We will eventually build a supervised model, maybe using PLS or some other supervised method to do this in the future. So stick along this journey. And then if we look at the data frame where we actually just specifically looked for peaks or filtered the data based on peaks, you can see this has done a significantly better job at clustering based on the gram positive or gram negative, likely because we're getting less noise and able to focus more on the signal where the signal was strong. So here, component 1 versus component 3 is pretty well separated. It is interesting that we have a cluster, sort of another cluster within the gram negative. Might explore that later. Now you see the benefit of being able to separate your data and how easily we could build these data processing chains to accelerate this even further, particularly if you're running multiple studies and all you want to do is drag and drop your data. If you want to be notified when that video comes, subscribe to the channel. If you enjoyed the video, like, and I'll see you in the next one. Peace.